Ah, I finally see names.
Hello, Professor.
Hi, where am I at now? I see all the names finally.
Okay, so you got 23 participants. I'm gonna start my video. 1 second. Same thing as last time. Click
What do
on
I
share.
do? Click everybody out of here?
No. Just green button. Share screen. Same as always.
Yeah. I'm hitting it, but I think they see me now.
No, you don't have your video enabled.
Oh,
We will figure that out. Don't worry. Just
all right.
green button that lets you share your screen.
Let me get rid of Chu Zhang. I see him smiling. All right, I'm clicking him out. Ah,
So yeah, do you see a green button with
on the
screen
left
sharing?
side, next to recording,
Uh,
or share screen.
Share screen.
That was covered, sorry.
Yeah, it randomly appears and disappears. It's annoying. You have to move your mouse around it.
All right, I'm sharing, but nothing's happening.
Do you get a blue little button on the bottom right?
Oh, now there's a different share. Okay, now the blue share. Okay.
Yeah, there you go. I'm going to request remote access and I'm going to set everything up. So
I should, I'm going to throw Mr. Zhang out. No, it doesn't matter. Go ahead, Ray. So share, I'm going to approve on you as usual.
Yep. Okay. So yeah, now I'll just set up the lecture materials and then you can move on with your clickers. So is, what's his name? Is he here?
I'm here.
Oh, Anvin. Yeah, perfect. Come on, Chrome, you can do it. Okay. Okay.
GitHub. Do I need to get rid of all the student icons in order to be able to see my notes? I think so.
No, you'll be good.
All right.
And like I said, always, the little window you see on the side, you can move it. So, yeah. But it doesn't matter. You'll be able to see most of your notes. Let me just
All right.
go here. And what lecture are we on today?
3.
Okay. Language, it's set through. Okay.
Yeah.
Also 4? Might as well open it.
Yeah, open it. Maybe we get to a few pages.
Okay, sure.
3's got a lot of definitions.
Okay, so let me just go to view.
And we'll get to Turing machines in 5, and by then I would have, I'd be an expert at whatever I need. Back to 3.
Don't worry, I'm just setting them up so that you can easily switch between
right.
them or whatever. And then finally the last one, review, present.
Oh God, 6? No, we're not going that. Go ahead, that's fine.
So yeah, we have 3, 4, and I think this is lecture 6. I might add lecture 5 later on.
All right, but 3 and 4 will keep us busy.
Yeah, so now that I've done this, what I'll do is actually, you know what, let's make this full screen, just because might as well.
How come I only get the student names? How come I can't get their faces?
Because they have
their cameras on?
Yeah, they have their cameras off. You can ask nicely.
Because then I would recognize. I never remember people by names. I always get them by their faces, and 20 years from now, I'd remember their faces.
Give them an incentive. I don't know.
All right. We'll do that another time.
Okay, so now I'm going to give up remote access.
And wait a minute, before you do, I need to get rid of their faces. That's taking up a lot of my screen.
Is it the little thing on the side that's like little box?
It's like, yeah, it's a rectangle box, a rectangular box. And inside the rectangular box is a bunch of squares.
Okay, I remember telling you, you can move that box anywhere else on the screen. It doesn't matter. It won't take that much space. As students, right, we can't see that box. They'll see your notes in its entirety. And if it's obstructing your view, you can move the box.
Let's see. Yeah, I can move it right off the screen?
Yeah, you can move it right off the screen.
All right, I'm throwing them on the floor. Good, I'm happy now. Now what?
Now I give this control to the clicker so that everything works. So I'm going to give up remote control access. And then Anvin's going to act as
Anvin,
click.
okay.
Yeah.
All right, I got to get rid of Mr. Zhang. He's not my clicker.
And yeah, so once Anvin can, get remote access and he can start doing the
All right.
clicking,
I'll
I'll
leave
be
you.
here. I'll be here for the next 5 minutes. After that, I'm leaving.
No, that's cool. Once I get going,
Yeah.
Anvin to remote control. So yeah, I approve he can share. All right, and do I need? I'm okay now.
Middle of a lecture.
Are you in class?
Yes.
Anvin, you there?
Yeah, I'm here.
Okay. Oh, you can't see my beautiful face. Tell him to put my face. You got it maybe. Where's the icon for my Hawaiian scenery? You can see that?
No, I don't see. You don't have your camera turned on.
So start video, huh? Okay.
There we go. We see the Hawaiian tree now.
All right, then I'm happy. All right, I guess we're okay now. Anvin, so lecture 3, guys, a lot of definitions. Sorry, that's the way we said that at the beginning of any course. So you can click Anvin. Again, these are all the definitions from the first 2 lectures. We know an automaton is a boring guy. Finite state machines can't solve some problems. That's just the way it is. And push down automata. I don't know. Lately in the dictionary, they're letting the plural be automatons. I should call up Professor Burr. He retired before your time. He used to yell at me for writing that. Recognize a language. It means we have a device that's capable of saying yes every time a string is in the language. Be careful. We made a big I don't like to use the word recognize. The word accept and the word decide. Somebody help me. What's the distinction between deciding a language and accepting a language? And we're going to agree not to use recognize because then it gets confusing. So what's the distinction between accept versus decide a particular language? Somebody help me out. You got to turn your mute off in order to answer that. You could put it back on again. I don't mind. I got 46 of you out there. Nobody's willing to answer? Good, I'm taking a water break. I'll be back in 10 seconds. Yes. Who's there? Nobody wants to answer? All right, hold on.
Doesn't accepting a language mean you don't have choice? If you're deciding, you're choosing if you want the language or not?
You lost me. Accepting a language means you don't have a choice. What does that mean?
Well, I mean, what are you asking for? You're asking like accepting a language that...
Versus deciding. What's the distinction between those 2 verbs?
Accept you're given a language and decide you're not given a language to choose from.
Oh, I'm going to beat you guys up. When you have an acceptor for a language, that means you're given a string and you have your acceptor. I don't know what it's built out of, but this machine, this algorithm accepts some language L. That means whenever a string omega, I like omega, I told you that. When you're given a string, the acceptor can say yes if the string is in the language, And it can say no when the string is not in the language. Acceptor. A decider for a language can say yes if a string is in the language. And if the string is not in the language, the machine does what I'm doing. Can you see what I'm doing with my hands? I'm throwing them up. I don't know. You can wait. You can wait. But a decider is not going to say yes. It'll say yes if the string is in the language, but it can't say no. It just doesn't say yes. Your midterm is going to have that question, I promise. So you got to be able to tell the difference. I don't have to be able to tell the difference. You do. All right, peace. And then click to another one. All right. So we've been going through 3 models of computation. Whenever I didn't screw up our Zoom connection, this is what we were talking about. Finite state machine. You have a tape, single tape, and you have a control unit. And the machine, you're able to put a finite amount of data on that machine. We're up to 47. Okay, that's what the clicking is. But you can't get extra tape. You fit your string on the tape. Don't be asking for more tape. It's not going to exist. So finite state machine, finite amount of memory. So when you had Columbo asking for one more thing in that crime drama from many years ago, he's not going to have enough paper to write everything down. So you can write as much as you can write, and then you're stuck. A push down, excuse me. Recognizing, I'm allowed to use recognize, don't you? Recognizing the language consisting of well-balanced parenthesized expressions. A finite state machine can't do that. You can build a machine to recognize the language consisting of one, I guess that's your left, one left parenthesis and one right parenthesis. 47 left, that might have been Ray. So a left and then a right. But don't go telling me the number of parentheses is arbitrary. You're not going to be able to build a machine to recognize that language. Push down automaton. You got your input tape. You have a control unit, sort of the brains of the operation. You got 2 heads, one to look at the input tape symbol, one to look at the symbol at the top of the stack. And now we're ready to fly. We can recognize well-balanced expressions, parenthesized expressions. But again, we're coming to Turing machines, the next chapter, I think. And then we'll be writing them together. I'm learning how to write them on the screen since I have a touch-tone screen. I'll show off next time, another time, we'll see. So a Turing machine, you have an input tape, which is unbounded. We're going to see in chapter 2, we get to much later. We do 9, 10, we come back to 2. Various models of Turing machines. One tape unlimited, one tape unlimited in both directions, and multiple tapes, multiple dimensions, multiple heads, who knows? So,
Professor, when you say tape, what do you mean by tape?
Tape, if I want to multiply 2 numbers, I take a piece of paper, let's suppose, there's the paper, you saw me draw it. I got a pencil. What do I have? Here's my pen. I write down 120, I'm writing backwards, I'm sorry, I'm not good at writing backwards forever in a mirror. So 123 times 241, boom. And I'm writing with my pen on this 2-dimensional sheet of paper. We don't use, well, you could have a 2-dimensional tape, but that's besides the point now. We got this piece of paper, and what we're gonna do is divide it up into little squares. Bing, 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 bing. And when you run out of, the 80 characters, whatever, then you go to the second line, boom, boom, boom. So the pen permits you to write on a piece of paper, And obviously, when we write as humans, it's two-dimensional writing. Boom, boom, bing. With a Turing machine, to start out with, we're going to assume we got a scissor, and we cut the paper into a single tape. I see. Whenever somebody comes in or leaves, I get a bell at my head. Okay, so we mean the tape is our analogy for a two-dimensional sheet of paper. Write whatever you like. When you run out of space, write again. My name is Stephen. You know, so I'm writing in one dimension. That's what I mean. If I'm multiplying, no, I can't do it. Right backwards. 231 times 486, boom. I'm writing in two dimensions. So what we mean is we're writing inside cells. What's a cell? It's a square piece of paper for now. And you could put one symbol in there, S. You can put another symbol next to it, T. I know I'm writing backwards in your frame of work, but otherwise I go nuts. The E, and we'll shorten it, VE. So you're putting one symbol, an S, a zero, a dollar sign, into one unit square of paper. Obviously, we're not going to need paper in this course. We're doing it theoretically. Am I okay? Did that make sense?
Yes, it did. Thank you very much.
Okay. So Turing machines, we can multiply. You want to get the square root of a number? You learned how to do that in middle school. We can do square roots. So we saw there are some problems not solvable on a finite state machine, recognizing well-balanced parenthesized expressions. Some problems are not recognizable on a pushdown automaton. You can recognize well-balanced parenthesized expressions, but you can't recognize a string like a to the n. See, now I can go backwards, which is correct for you. A to the n, b to the n, c to the n. Finite state machine, you could recognize NAs. We don't know what N is, but it's an arbitrary number. The finite state machine has no trouble with that language. A, was it up there? A to the n. Give the finite state machine A to the n, B to the n. The pushdown automaton doesn't know what to do. I'm sorry. The pushdown automaton has no problem. Recognizing A to the n, B to the n is a piece of cake. Every time you see an A, put an A on top of the stack. What'd you see, 17 A's? Okay, I got a stack with 17 symbols on it. I know, I didn't forget. You got the bottom stack marker, but we're just keeping track of the important stuff. So 17 A's. Then we change states. Why are we changing states? Because we saw a B. If you don't change states, you're not going to recognize this language. Every time you see a B and there's an A on the stack, please be nice enough to take the A and throw it out. I told you, Greek restaurants now expect you to just throw flowers. Throwing plates gets dangerous. When I was in Greece, we threw plates. Somebody must have got hurt when I was there. Who knows? So a pushdown automaton, a PDA, can recognize the language A to the n, B to the n, where A could be a left paren and B could be a right paren. And we said, obviously, you want to be able to recognize left, right, left, right, left, left, right, right. Those are all well-balanced parenthesized expressions. We said when we get to pushdown automata in chapter 10, we'll be able to do that. Then with a Turing machine, A to the n, B to the n, C to the n, the Turing machine can recognize NAs and NBs. All right. So suppose we recognize it. Now the machine has an empty tape and the first C comes in. What the heck do you balance it with? You don't have any memory of having seen A's and B's. You threw them away so you could recognize equal number of A's, equal number of B's. Now you're stuck with the question, what the heck was the value of N and you need to recognize NCs. You can't do it. I'm sorry, you could do it. Let me take it all back. A push-down automaton is not going to be able to accept that. A to the N, B to the N, C to the N. A Turing machine, and we'll see that maybe by the end of next week, we will build a Turing machine to recognize L for language, consisting of NAs, NBs, NCs. That we can do. So there were problems that are unsolvable on a finite state machine, but could be solved on a push-down automaton. Likewise, there were problems that could be solved on a push-down automaton, but could not be solved on a finite state machine. And finally, A to the N, B to the N, C to the N, a push-down automaton is not powerful enough. It doesn't have the wherewithal to accept that language. Turing machines can indeed accept the language A to the N, B to the N, C to the N. To find a problem that a Turing machine can't solve is going to take a little more time. We need to get a little further along in our discussion of theory. And then we'll be able to see Turing machines have limitations as well. And some of the problems that Turing machines can't solve are in fact useful and important to computer scientists. But we're not there yet. Are we okay? Somebody say yes.
Yes.
Thank you. That's all I needed. I'm an insecure guy. You tell me yes, I'm very happy. All right. Anvin, give me a click. Ah, don't click. A string or, go back, I'm sorry. A string or word. There, that's it. That's what I wanted. All right, we'll go from, I see you clicked before I saw it. So alphabet. An alphabet is a finite set of symbols, usually non-empty. Yeah, you could have an empty alphabet. What are you going to do with it? So the capital A1. By the way, these are arbitrary names. Hold on. I think we took away my scotch bottles from the first lecture, so you can't see them. If everybody gets an A in the course, then we'll go empty my bottles here. An alphabet, finite set of symbols, usually non-empty. So A1, again, that's arbitrary. Make up your own name, I don't care. Usually a capital letter. So A1, the English alphabet, A, B, C, D, up to Z. If it's French, you got to throw in accent aigu, accent grave, circumflex. I'm just showing off. I can't do more than that. So A2, binary alphabet, 0 and 1. Okay. So now another, again, I'm sorry, we got to get a lot of definitions down. I promise we'll be able to fly once we know all of these. So a string or a word. Back in elementary school, we always looked up words in the dictionary. Now you go on Google and you punch a word in and see what it means. You can even ask for, you know, what does it sound like, this word? Onomatopoeia. When the word sounds like the thing that it's modifying. Ah, I remember that. So a string or a word, we use them interchangeably. So we're not talking necessarily about one of the 1,025,000 words that are in the biggest dictionary you could imagine, you know, the Oxford Supreme Edition. We use string, in formal language theory, we use the term string and word interchangeably. MOM is a word, MOM is a string. That's so, just because it's not in the dictionary doesn't mean it's not a word. In this course, obviously, if you go to your English class and you say, my computer science professor said that TTY was a word. No, I didn't say that. If you take it in the context of formal languages, TTY is a word. So in this course, throw away your old meaning for the term word and string. Okay, Anvin, give me a click. Okay. Whenever mathematicians get the objects, they want to play with them. They go into their sandboxes and they throw rocks around, right? Whatever mathematicians do, or logicians. So the way we're going to play is using concatenation. You want to talk addition of integers? 3 plus 7 is 10. If all you have is strings, then the operation we're interested, binary operation. All right, we'll more of that in a moment. Concatenation of strings. So we said we like Greek letters in this course, alpha and beta. Let them be strings. Then alpha circle beta, in order to form the union, not union, but apply the operation of concatenation on the two strings alpha and beta. Take them and smack them together with no space in the middle. So the string alpha concatenated with the string beta is the string alpha beta. It's a good thing we don't have a blackboard, but I'll be writing, many of you already know the software that one uses. But alpha circle beta is the new string alpha beta, okay? So if alpha is the string spider and beta is the string man, then the concatenation of alpha with beta, which we would read in the future as alpha circle beta, is the string Spider-Man. So take the space away and squash them together. So concatenation is a binary operation from S cross S into S. What the hell is that? So let S be the set of strings, then S cross S is the set of two strings, which they're allowed to be the same, why not? So S cross S into S. So suppose we're looking at natural numbers. What the heck? We have integers here. So we're looking at integers and the addition of integers. Z cross Z. That means we're going to take an element from the set of integers and what the heck, take one more element. So Z is this set here. Minus 10,000, minus 9,999. In 20 minutes or so, we'd be up to -1. And then go to the positive, start talking non-negative integers. 0, 1, 2, and in a few years, we'd be up to 1,014,000. So 2 plus 3, take the concatenation, well, we're not doing concatenation, we're doing addition. 2 plus 3 equals 5. So binary operation, binary 2, you take 2 elements from a set. In this case, the set is Z, the set of integers. So take an integer, 2, take a second integer, 3. The operation is addition. 2 plus 3, you end up, I'm over there. Your right, my left, is 5. So that's a binary operation. How about subtraction? Subtraction of integers. I'm sorry, subtraction of positive integers. So Z plus cross Z plus. Be careful, 0 is not a positive integer. 0 is a non-negative integer. So is subtraction of positive integers closed, which means is the result in the same set. So you're in Z plus cross Z plus. Okay. I keep thinking somebody's leaving or coming in, but then I don't hear any doors in the background. I have to get used to this virtual world that we're in. But okay. So is subtraction of positive integers a closed operation? Somebody help.
Are you
No.
talking about, oh, go ahead.
Sorry, because you can like subtract 3 from 2 and get a negative integer.
You get -1.
Right.
And -1 is not a positive integer. You're right. That's it. So subtraction of positive integers is not closed. We don't have closure because the result might not be in the same set. Okay. All right, we're getting there. We're cool. There you see, I knew that was coming up. I don't look ahead. I just remember this from 100 years ago. Okay. Oh, binary operations, the integers with respect to multiplication. That's an easy one. I'm going to do it. I'm going to say yes. 6 times 7, 42. 7 times 0, 0. That's okay. 0 is an integer. All right, number 2. I'm going to try. Help me if I screw up. The integers with respect to division. 10 divided by 2 is 5. 11 divided by 11 is 1. So it looks like we have closure. Anybody have a comment?
What about dividing it by 0?
Okay. And how about dividing by anything, like 10 divided by 3? How much is that? Be careful. I said division. I didn't say whatever the heck I would have said, you know. But what's 10 divided by 3?
So that's
Real division.
3 1/3.
So 3 1/3. Yeah, that you can do it, but is 3 1/3 an integer?
No.
There you go. So you come outside of the set. So in mathematics, if something is not true for all cases, then that's it. It's not true. I don't want to hear about the infinite number of cases in which it is. 10 divided by 2 is 5. 100 divided by 50 is 2. That doesn't convince me. The minute you tell me 10 divided by 3 is not an integer, all bets are canceled. This division is not closed under the set of integers. Okay. Now, Q stands for rationals. A rational is a pair of integers, and you have to promise me the second integer is not 0. If you don't promise that, I'm not going to listen. We know better. Back in junior high, we learned you can't divide by 0. So 10 divided by 2 is 5. 12 divided by 6 is 2. I don't think I can fool you twice. Wait a minute. 10 divided by, rational. The number can be expressed as a ratio of 2 whole numbers. What's the same question? What's 10 divided by 3 if we're in the set of rationals? Is that a rational? If you divide 10 by 3, what's the result?
Isn't it a rational number because you could write it as a fraction, m over n?
What's the fraction? When you divide 10 by 3, what's the fraction you get?
10 over 3.
And what's that equal to? Is that a rational result?
A rational number can be written as a fraction. So if it could be written as a fraction, then it's a rational number.
And 10 divided by 3, is that a rational?
Yes.
Wait a minute, I'm lost. I thought 10 divided by 3 was 3.333, and keep writing 3s. Where am I? I'm on the west side. So I'm going to run across the Hudson River and keep hitting 3s down there. When I get to Grove Street, I'm still writing 3s. Am I ever going to stop? I know all of you wish I would take the run out and then you can go to sleep. But no, you can't express 10 over 3 as a complete number. 10 over 3 represents something, but you never reach it. If you're telling me you're doing, what the hell are you doing? Div, D-I-V, that's not divided by. That's divided by and take the integer result or the rational result. then I'll go along with you. But no, 10 divided by 3 means 3.33333. I'm still running across to New Jersey. I should. I need to lose the weight. But you could put a little dot on top of the rightmost 3 that you put down, but that means keep going. No, that's not rational. 10 over 3, because you're never going to be able to stop. A rational number is one that can be expressed as the ratio of 2 whole numbers. 10 divided by 3, you didn't capture the number. You gave an approximation, 3 1/3. 3 1/3 is cool, but 10 over 3 is an irrational, because to fully express, unless you tell me the operation is div, div is different than division. It means take the integer part of 10/3, which is 10/3. All right, think about that. Yell at me during office hours, which again, I'm sorry, today we were still playing, Ray and I, definitely after class. Class ends at 4:45. You could stay around. The gentleman that I was chastising nicely. I'll explain further why that's not irrational. Okay, so Q stands for the set of rationals. You see it, -1/2, -1/4, so a rational, the rationals, excuse me, the whole set. You got ordered pairs of numbers, P comma Q. P and Q are integers, and you got to promise me Q is not equal to 0. If you do that, I'll buy it. But again, careful, 10 over 3, you never stop dividing. Your operation goes on forever. So
None,
yeah. Go ahead.
So none of them are binary operations.
The integers with respect to multiplication, that's binary. There were no exceptions. 6 times 7, we said, was 42. 0 times 1,000,000 is 0. I can't find, they're always, yeah. The integers with respect to division, that's not a binary operation, because 13 divided by 2 is 6.5, and 6.5 is not an integer. Closure insists that the result be from the same set that the operation was from. Okay, we got somebody who popped in. All right, I'm getting used to it. I need to see your faces. Having your name doesn't help. If I see your faces, I'll know whether I know you or not. All right. All right, Anvin, you can send us on. Okay. Oh, so formal languages, we've been talking a little. We got some more operations. Length of a string. Write it any of these 3 ways. Spell out length, yeah, lowercase if you prefer. The length of alpha, where we're using these Greek letters to represent strings. If you prefer capital L of alpha, or I know that the next symbol you're used to seeing as absolute value, we're going to buy it as length. So any of those 3 will stand for the length of a string. The number of symbols that alpha contains. The length of 0, 1, that's 2. 2 distinct symbols. Let me stop saying distinct. What's the length of 0, 0? Somebody? Careful, I didn't say value of 0, 0. What's the length of the string 0, 0?
Still 2.
2.
Yeah, 2. Okay. The length of bat is 3. The length of man is 3. So the length of, that looks like an A, not an alpha. So the length of A concatenated with B is equal to the length of A plus the length of B. The length of iron concatenated with man is, it's not length. Iron concatenated with man is the new string Iron Man. And you're right, I should not have put iron, I in lowercase. I don't know, this is not case sensitive. That's cool. So the length of iron plus, yeah, you got it. 4 plus 3 is 7, Okay. Anvin, you can take us to the next. We got a special string, since we're talking strings and alphabets, epsilon. Well, that's a funny looking epsilon, but it's the unique length. Epsilon is the unique length of string 0, whose length is 0. So put epsilon in brackets. So the length of epsilon is 0. You can't see it. It's there, but no, it's not. All right, so alpha concatenated with epsilon is the same as epsilon concatenated with alpha is equal to alpha for all alpha. Okay. Epsilon equals epsilon concatenated with bat. Yeah, okay. That's bat. So epsilon is the identity for concatenation. So of course, epsilon, circle epsilon is epsilon. All right. So somebody help. What's the identity for the natural numbers with respect to addition? There's 48 of, maybe they're counting me.
0.
There you go. What's your name?
Nor.
Weren't you in my summer class 1.5 years ago? No?
Yeah, I was.
All right, see? Where'd you sit? I should know that.
By the wall.
Okay, see, it's coming. The left wall, right? From my vantage point.
Yeah.
Where was it? Second or third row?
I think the third one.
Okay, because I'm trying to reconstruct portions of classes that I've had, students I've had. Because I can't see you. I see sounds. I don't see them. Okay. The integers with respect to multiplication. What's the identity?
1.
Yeah, you got it. Oh, multiplication of 2x2 matrices with real coefficients. And you know what the reals are. So what would be the identity for this multiplication?
1.
No, it's not 1. I see. Here's a matrix.
Wait,
It's a,
so the
what's in this 2x2 matrix?
Sorry, it's the identity matrix. I thought.
So it's I sub 2, capital I sub 2, and you got to put a 1 up there, a 0, a 1 down here, and a 0. So it's a 2x2 matrix with the 1s on the off diagonal. All right. That was close enough. Anvin, take us away. All right. So we got the notion of a string down pat, concatenation of strings. All right. So let the string alpha equals UVW. Okay. So we're forming a string as the concatenation of 3 substrings. So V is a substring of alpha. Ooh, I got a fly. Maybe one of you guys can knock it down with your fly swatters. Okay. Another definition. A prefix of a string is a substring that occurs at the beginning of that string. I hate when people talk that way. You must have some friends like that. That when you're saying something and then you put quotes around the word. Actresses do that. I don't know. A female actress or actor, when they go on TV, sometimes, I don't know, they put parentheses in space. Okay, it's too, I don't know. What's the word for that? Affected, A-F-F-E-C-T-E-D. So a prefix of a string is a substring that occurs at the beginning. What we mean, why I put quotes is, it doesn't have to be at the beginning. Let's get that straight. So alpha, suppose it's the string UVW. So U is a prefix of alpha. Okay. But how about the empty string? Well, the empty string is a prefix of alpha. Even though it's empty, it's still a legitimate string. Okay. Definition, a suffix. We get our quotes one more time. A suffix of a string is a substring that occurs at the end of that string. So alpha equals UVW. W is a suffix of alpha. I hope we're okay. So again, chapter 0 has all these definitions. You got to get it together on this. I'm sorry, I'm Vin. I was about to take the clicker. I'm not supposed to. That's your job. Go to it. Okay. So suppose we got the string alpha 0101 over the alphabet 01. Okay, that's nice. The prefixes of alpha, all strings at the beginning. I'm not going to look at my answer. I do that. And you could tell I'm honest because sometimes I fall on my face. So we got alpha. I got to get the question. Prefixes. 0, 0, 1, 0, 1, 0, 0, 1, 0, 1. I've been doing this too long. I forgot one. Epsilon. So we got a string of length 4, and there are 5 prefixes over this string. So the string has 4 characters, but we're not permitted to forget the empty string. Therefore, a string of length 4 has 5 prefixes. Go back to sets. Suppose I give you the set containing little a, little b. Okay, that's nice. You got a set with 2 elements. Then we have the empty set, the set containing 1, the set containing 2, and now which one did I forget? What did your discrete math teacher say? Nora, when you were sitting in that 3rd seat, you had a good-looking teacher in 104, I remember. I was always envious. What else is there? What are the prefixes for 0101 that I failed to mention? Careful, Nora. Once I know your name, you're in trouble. Victoria, you're there too somewhere, right? Yeah, go ahead.
You have. I don't think you include. No, never mind. You have all of them.
No, I forgot one.
What?
I gave you 4 subsets.
Is it epsilon?
I gave you that.
Yeah.
I gave you epsilon. The set.
You said AB, right?
Wait a minute, we're dealing with 01. How'd you get AB? Oh, wait a minute. You're right. You're right. I don't know what I'm doing. I didn't have a strong enough coffee today. That's what it is. I guess I did say it. Well, let's go back to 0101. Then the subsets I would have mentioned were the empty set, the set containing 0, the set containing 0 and 1, the set containing 0, 1, and 0, the set containing all 4 of them. I didn't count the set itself. I don't feel like listing all the subsets, but it's clear that I'm missing the set itself with all 4 elements. Okay, so.
Sorry, don't you already have that 0101?
I didn't say it again. I mean, the set containing everything is said to be a subset, but not a proper subset. Okay, so you got to include the set itself, whether it's 0 and 1 or over A and B.
I'm sorry, I'm still a little confused.
No, you did include it.
Yeah.
I didn't mean to.
You said 0, you said
Wait,
A, and then
I'm
you said
sorry.
AB.
Somehow I went from prefixes to subsets. Help me out. Who's talking now?
Okay, this is Saiful, and you said the set AB, and you mentioned 0, A, and AB. You mentioned all of them.
Sides,
I'm mixing up my alphabets. Either I have to stick with 0, 1, or I have to stick with AB, A and B. And I screwed it up. So somebody get me out of my muck. Stay with what we see in front of us.
Okay, so this is 0, 1.
Go ahead.
So if you said 0, 1, then you have the empty, then you have 0, and then you have 0, 1.
All right, but if you consider the string, the whole string 0, 1, 0, 1, sometimes we say that's not a proper substring. Okay. Okay, and prefixes. Epsilon is a prefix of every string. So the complete set of prefixes of 0, 1, 0, 1, you see the list, the third bullet. Epsilon, 0, 0, 1, 0, 1, 0. And finally, the prefix that's not a proper prefix, 0, 1, 0, 1, because it's the whole prefix. I was taking the analogy with sets, but I confused myself. The complete set of suffixes of 0, 1, 0, 1. The first four, epsilon, 1, 0, 1, 1, 0, 1, those are proper prefixes, whereas 0, 1, 0, 1 is a prefix, but it's not a proper prefix because it's the whole string there. All right, look that over. All right, Anvin, give us a whirl.
I understand. It's one of the main reasons why I pursued it, that it was a very a lot of opportunities. However, this is the worst job to do. You know less about coding and you want to do it.
Tell the gentleman who's giving a lecture on jobs to turn his mic off.
Programming is like
Anvin, can you click to the next slide?
Like dribbling a basketball and shooting a basketball or throwing a football is a skill. Programming is a skill.
All right.
And you want to become a professional who does it 8 hours and some days 10 hours a day.
Who's got their
you're gonna have
YouTube on?
to enjoy it. I don't know too many athletes.
Peter, your YouTube is
only
on.
Play basketball for the
Turn
money.
YouTube off.
Of it, and then they end up being really good. And
Thank you.
money. But think of programming that way.
No,
Bruh.
Who put YouTube on?
Your YouTube is on.
Are you protesting that the class is going on too long? Who is that? So you can't find him and hit him on the head either, because he doesn't exist in real space. He's one of these 48 creatures. At least put headphones on if you're going to listen to videos while I'm talking. Okay.
He's muted now. He's muted now.
Thank you.
Professor, one
Yeah, go
last
ahead.
time.
Yeah,
So
go ahead.
back to the prefix. We were missing one, right?
A string of length 4 has 5 prefixes. Only 4 of them are proper prefixes. If it's a prefix but it's not a proper prefix, then it's the whole string itself. Is that okay?
Yes, thank you.
Okay. Oh, concatenation once again. Concatenation of a set of strings. Oh, the set A, let it be 0 and 1. The set B contains A and B. Then concatenation of sets. A concatenated with B, or A circle B if you prefer. It's the set of all strings omega, such that omega equals alpha beta. Alpha is an element of the set A. Beta is an element of the set B. So A circle B equals 0A. That was the first element from the set cap A to the first element in the set cap B. 0A, 0B, 1A, 1B, okay? And again, the length of the set of, the length of the string A, cap A, if it's M, and the length of B is N, then the length of A circle B equals M times N. Okay, and if you want to prove that, you got 2 ways to do it. I'm going to leave that an open question. I'd rather put that on a midterm. Anvin? Okay. Oh, A squared. That's the set A concatenated with the set A. Or neater, A circle A. And if A is the set containing 0 and 1, then A circle A is the set containing the 4 strings, each of length 2. 0, 0, 0, 1, 1, 0, 1, 1. Okay? A to the third power, that's A circle, A, which is 0, 1. You got it. And that's all strings of length 3, of which there are 2 to the third or 8 of them. Okay. Okay. And what's A to the 0th power? All strings of length 0. How many strings of length 0 do we have?
1.
There you go. So A to the 0th power is the set containing epsilon. Okay. Careful. A to the 0th power equals 1 and not 0. We got to make sure we understand that. Okay, somebody, Anvin, click it for us. Kleene closure. The beginning of the 20th century. That's way back in 1900. You know, I don't know. Did the 20th century start at 1900, or did the 19th century end at 1900? Don't ask me. I can't deal with that today. But Kleene, along with Turing and Church, were 3 of the big honchos of the last century in computer science. And yeah, this is more like mathematics than computer science, but it's the beginning of our discipline. So the Kleene closure of an alphabet. We use terminology A superscript star. So if I say A star, please put the star up top. The superscript, you might be tempted to say the exponent, but that's like the superscript. So A star, I mean A superscript star. We got that by now. A star is a set of all strings that one can form using the symbols from an alphabet. So if A is the set containing 0, 1, then A star is the union of all these sets we see coming up. A superscript 0, A superscript 1, union A superscript 2, and so on. And that's that line, all those unions, we can shorten it. The union as I goes from 0 to infinity of A to the ith power. Okay? And that's the set containing epsilon. And by now we know the set containing epsilon is not the same as epsilon. Epsilon means the empty string. The set containing epsilon is a set with one element in it. Make sure that makes sense to you. Union the set with 0, 1, and keep going like that. So finally we get the Kleene closure of the set A is what you see on that last line. It's the set of binary strings of each and every length possible. The string of length 0, we denote it with epsilon, and keep going. Yes, you got to give me your name.
Mikhail.
Mikhail.
Yeah. Is containing.
You told me last time. What country you're from? Is that Russia?
No, Israel.
Oh, I'm sorry. And you told me the city?
Yeah, Jerusalem.
Okay, yeah, you did. Okay, go ahead.
Yeah. So about the epsilon, what element contains the epsilon that you mentioned in the last one?
All right, hold on. When I was a doctoral student, I was always busy. I couldn't do anything, just study all the time. I was a bookworm. And anytime there was a holiday, I would tell my mother, tell the relatives that I can't make it. You know, I would be studying, and I wasn't lying. I wasn't. So even my mother, she knew, don't expect a present on Christmas Day. I would get her a lovely present, but it might be a week after Christmas. So on Christmas Day, I would give her a beautifully wrapped up box, but there'd be nothing in the box. So I'm giving her the empty box with beautiful wrapping paper. So that's like epsilon, the set containing epsilon. I'm giving her a gift, but the gift has nothing inside of it. So I had no idea what you asked. What was the question again?
Yeah, you said picture the difference between an empty set, which is represented by epsilon, and then we have the epsilon.
The set containing the empty set, which is my wrapped up box with nothing inside of it. That's the set containing the empty set. But that's not the same as not giving her a present, which is epsilon.
Right.
Not that she could use an empty box with wrapping paper, but that meant Stephen hasn't forgotten his mother, but I had no time to go shopping. She understood that. So there's the empty set, that's epsilon. And then there's the set containing the empty set. Okay.
I remember that.
They're distinct. We're gonna have to think that way. All right, Anvin, go ahead. Positive closure. So we got the Kleene closure. If I give you the binary alphabet, that contains 0 and 1. Then the Kleene closure of the binary alphabet is the set of all binary strings, including the empty string. But the positive closure is the set of all strings, binary strings, but you got to promise to take away the empty string. What the hell are we saying? So positive closure of an alphabet, we write it as A superscript plus. So A star is the Kleene closure. A plus is the positive closure. Okay, so A plus, the set of all strings of, I know, we're not going to do this, I promise. We won't just do definitions for 4 months. Once we're done with the definitions, we'll have plenty of theorems and automata. And you're going to tell me, you know, I missed the definitions. They were easier. But okay, we'll live with it. So the positive closure of an alphabet, A plus, it's the set of all strings of length 1 or greater formed from the symbols of some alphabet. A plus is the union as I goes from 1 to infinity. Careful. The Kleene closure, we went from 0 to infinity. Now we're going from 1 to infinity of A to the i-th power. And now the notes, there should have been some space there, of course, which is the same as A star minus A0. Careful, when I pause like that, I'm talking superscripts. So you got every binary string, but then you take the set containing the empty string away. So A plus, the positive closure of the binary alphabet, you see it written on the bottom. 0, 1, all strings of length 2, of course there are 4 of them, and so on. Notice the set containing the empty string is gone. So you have A star, if A is the binary alphabet, you got all binary strings, even of length 0. But A plus, please take away the empty string. Don't take away the empty string. Take away the set containing the empty string. This is all in chapter 0. You're going to love it. Okay, Anvin, hit us again. Languages L over some alphabet sigma. So what the heck is a language? L is a subset of sigma star, okay? So a language is a subset of the Kleene closure of an alphabet. So there you go. It says it right there. So let sigma equals the set containing 0 and 1. Then sigma star, that's Kleene closure, is the following set. Epsilon, I'm sorry, this is elements inside the set. You have epsilon, 0, 1, etc. And what's the longest string in the set sigma star? Somebody help. The shortest string is epsilon. It's of length 0. But what's the longest string?
3.
Infinite length.
That's it. It's unbounded. If you don't want to say infinite, just say it's unbounded and we get the point. Okay. Anvin, hit us again. So languages. Hold on. This is actually vodka in the bottle. I need it, you don't. Okay. So language expressions. We'll be dealing with languages as we deal with various automata. And again, we equate languages with problems. So computer scientists will always transform a problem into a language. We don't care about languages. We're not English majors, but it's a concise way to represent a problem. Okay, L1, let that be the language 0 to the n. And by now we stop thinking of exponents. 0 to the n means n copies of 0. We know that by now. We stopped asking. So L1, 0 to the n, 1 to the n. You have n copies of 0 followed by n copies of 1. Careful, that slash such that n is greater than or equal to 0. Okay, so that's called a language expression. A concise way to represent a language, where a language is something we use to represent a problem. All right, so L1 is a set of all strings consisting of an equal number of zeros and ones, but you got to promise me all the zeros come first. So L1 contains epsilon, 0, 1, 0, 0, 1, 1, and I refuse to say the next. I'll say 0 to the third, 1 to the third. How's that? And dot, dot, dot. To a mathematician, that stands for and so on, and so on, and so on. Okay? So L2, let L2 be this set of strings omega where the characters come from the alphabet 0 and 1. Well, these are strings coming from the alphabet 0, 1 star, such that the number, this is, be careful with this notation. N sub 0 omega, the number of zeros in each string omega has to be equal to the number of ones in each of these strings. Okay, so are L1 and L2 describing the same language? Did I write that wrong somehow? Somebody help us out. Did I write the same thing twice by mistake? L1 contains the same number of zeros and ones, and L2 each string in L2 contains the same number of zeros and ones. What's the difference? Maybe that question's too easy. Some of you cheated and you clicked your own machine since you have copies of these notes. So you're embarrassed to answer such an easy question. All right, I got you. So L1, the zeros must precede the ones if there are any zeros, if they exist. In L2, the zeros and ones can be in any order, but you have to promise the number of each is equal. All right, Anvin? Okay, so here it is. The number of zeros equals the number of ones, but their order of occurrence does not matter. So L2, epsilon, 0 zeros, 0, or you want to say no zeros, and 1, 1. Then you also have 1, 0. Careful. The third string here, same number of zeros and ones, but the ones, well, the 1 comes before the 0. So L2, which is a larger language, L1 or L2?
L2.
Yeah, because, oh, Annie, get your gun. So the song I'm thinking of is, anything you can do, I can do better. No, you can't. Yes, I can. Well, I don't know. That was a Broadway show. I didn't get to see it. God knows when Broadway comes back again. So we'll see. Then I'll even dance for you if we have a class together. All right. No, already I've been told by a good friend, she thinks I have a wonderful speaking voice, but she said, don't quit your day job. She doesn't think much of my singing. All right, that's her. I'm sure you love when I sing. observe that every string in L is also in L2. Yeah. So L1's a subset of L2. Same number of zeros and ones in both languages or each language, but in L2, we can have arbitrary order on the symbols. Okay. So L1 is a subset of L2. All right, Anvin, give us another click. We got, I think, 6 more minutes. We're making it. Oh my God, and Zoom didn't screw up yet. I told you there would be a day that we'd finally get the wrinkles out. All right, here's a third language. L3 is the set of all strings omega, such that omega is an element of the Kleene closure of the binary alphabet. You don't like when I say that? So L3 consists of zeros and ones only, but omega equals omega reversed. Okay, so omega R, I don't know, do we have to, I guess we should say it. Omega superscript R is the reversal of the string omega. So 0, 1, 1 in parentheses, the reversal of that string is the string 1, 1, 0. Okay. All right. So L3 consists of all binary palindromes. In English, we said this earlier. A palindrome is a string that reads the same way forward and backwards. All right, we used the examples last time. Mom, M-O-M, pop, P-O-P, radar, R-A-D-A-R, and so on, and so on, and so on. Okay, so a palindrome is a word that reads the same way forward and backwards. Palindromes in English, all right, did I say dad? Who knows? Madam. So L3, binary palindromes, careful. Epsilon. And don't write the epsilon backwards. That's not epsilon, that's some other symbol. So epsilon 0, 1, you got the idea. These are all palindromes. Anvin, let's, the relationship between languages and problems. A problem specification. I still got 3 minutes. Don't run away yet. So suppose it's the language of primes. An instance of a problem is an example of that problem. So this is the problem of primes. An instance, an integer n, and then you can ask a question. Is n a prime number? Okay. So this is a decision problem. Careful. The answer is yes or no. I don't know. You got to tell me what the integer is. All right. Okay, Anvin, click it again. So the language of a problem, bad grammar. Put the word in your notes. L sub prime, that's the language of primes. 1 to the p, that's p copies of the symbol 1. All right, we're getting used to this notation, I hope. Such that p sub prime, or p prime, excuse me, is the set containing 1, 1, comma 1, 1, 1, comma 1 to the 5th. Okay, and that's an instance of the problem is n prime. Did I forget one? If I'm only giving you the primes from the beginning to 5, did I leave any out? Isn't 1 a prime? What did your math teachers tell you? Maybe in calculus. Didn't they write down 1 as a prime number? No, a math professor would never do that, especially not a math professor. So 1 is not a prime.
1 is like a special case.
There you go. You got it, babe. 2 is the smallest prime. Okay. A prime is an integer greater than or equal to 2 that has no factors other than itself and 1. So yeah, 1's allowed to be a factor of 3, but okay, you got it. I'm not going to confuse you. So if omega is an element of the language of primes, then that number must be a prime number. So if I ask you, is 1 to the 5th a prime number? The answer would be yes, because it's in this language. Okay? So the membership question, given a language and given a string, is that string in the given language? So that's the membership question. Okay? And the problem specification and the corresponding language for a question, is the integer n a perfect square? 9 is a perfect square, 16 is a perfect square, 25 is a perfect square. So you should be able to write this question as a language and be nice enough in there to put 1, comma 4, comma 9, comma 16, comma 25, comma 36. I can go on all year, but I hear some of you, you're checking your watches and you're saying, didn't he promise to shut up at 4:45? Yes, I did. Maybe my watch is 2 minutes fast, but we're going to let you slide. So we'll polish up. Anvin, let me take a peek at the next slide. All right, we'll do that next time. So we made it through a class and Zoom did not crash on us. We're getting good at this. You don't have to run away. I'm going to stop talking, but if you have any questions, I'm here to answer them. Okay, so I'm not going anywhere. All right, class is done, but again, we'll pick up on lecture 3 on Monday. Wait a minute, Monday's not a holiday, right? When? Oh yeah, the Columbus Day is in October. So we're good. Go ahead. What was that question?
I have a question. So how many, are we gonna do a lot of proofs in this class?
Some.
Some? Okay.
It's not just math. Maybe it seems like that now, but this is the math we're gonna need in order to talk about the theory. So we're gonna look at automata and we'll build automata, and you're gonna have homework using JFlap. We said that's a language where you can actually simulate these machines. You'll use JFlap to build a finite state machine. You'll use JFlap for PDA, and we'll build Turing machines out of JFlap. And you'll see why it's nice to have those languages to simulate the problems that we'll solve with them.
Professor, I have a question regarding Cleansy closure.
Hold on. You're from, you're Russian. Oh my God! It wasn't Malik. What was your name?
Aliyah. My name is Aliyah. I'm not Russian.
Oh, then I didn't talk to you earlier today. Aliyah, spell it.
ALIAA.
Wow, 2 A's in a row. Go ahead, Aliyah.
All right. I have a question regarding the Cleansy closure. So the positive closure does not include the empty set. Is that right?
Does not contain the empty string.
The epsilon.
That's correct.
However, the other one with the asterisk, I think
that's the Kleene closure. You take a set, I'll use capital A, what the heck, and then put a star up top. We're talking the Kleene closure. Kleene closure, the set of all substrings. Positive closure, the set of all substrings, but be nice enough to take away the empty string.
Okay, sounds good. Thank you.
Sure.
Professor?
Yes.
It's 4:45. If you want to ask questions.
No. But I need to keep them, I need to be able to talk to them.
Yeah, I'm just saying that I'm just giving you a reminder that once you're done with the lecture and everything, on the bottom right side, you're going to see a button that says end meeting for all.
Yeah, so I don't want to do that yet, but before I leave, I want to click that.
Just make sure to do it so that I can get the lecture recording and I don't have like a 12-hour video I have to edit.
Yeah, Ray was complaining about that. I think it was his fault. Let's yell at Ray, not you. Okay, so end, what do I do? End?
Yeah.
Just end the meeting.
For all, but not yet. Like ask.
No. So when the last question comes, after that last question.
Yeah, you'll see a button. It'll say, it's like a red button. You can't miss it.
It's stop the share or stop the meeting?
No, you'll just see it. So when you When you click stop share, right? Remember where you see the options participants, chat, share screen, record, reactions, right?
Yeah.
Yeah, so on that little window, on the bottom right side, you can see a red button that says end meeting for all. So just make sure to click that. When you end the meeting for everyone, then it'll start recording, it'll convert the recorded video lecture.
Okay, thank you. All right.
Okay, I'm gonna leave now.
All right, ciao. Who's got more questions out there?
Yeah, I got a question.
Go ahead. Well, you got to give me your name.
My name is Chu.
CHEW or CHU?
CHUE.
Wow. Okay, go ahead.
All right, so this was regarding the rational number of 10 over 3 that you were talking about earlier.
Yes.
You said it was not rational, but I think it is rational because you could form it with a fraction. It's 10 over 3, so therefore it is rational. You could form it with
I didn't mean the expression 10 over 3. I meant 10 divided by 3.
So do you mean like the integer? Wait, what do you mean?
I mean the number that you get when you take the integer 10 and divide it by the integer 3. You don't get 10 over 3. You get 10 divided by 3, which is 3.333, and you go on forever.
But that's still rational, is it not? Because you could form it with fraction with integers. Like, but let's say like square root of 2.
No. You cannot express it as the ratio of 2 integers unless you lose some precision.
So you could say 10 over 3 is like rational, but 3.3.
You could say 10 comma 3 is a rational number with 10 as the numerator and 3 as the denominator. I'll buy that. But if you're telling me to divide 10 by 3, I'm telling you the result is not a rational number.
So the result is not a rational number, but like let's say 10 over 3 is rational.
Now you got to tell me what you mean. Now you lost me. What's 10 over 3? Are you taking 10 and dividing it by 3?
Yeah.
Then I'm telling you the result is not rational.
Because like I'm also looking on like online and stuff. It says that 10 over 3 is rational. I'm gonna read a quote directly from someone, and it says a number is said to be rational if it is a form of P over Q, where P and Q are integers, where Q is not equal to 0.
That's correct. But if you're dividing 10 by 3, then the expression you get to represent 10 over 3 is not.
Oh, okay, yeah, I get it, okay.
We're not saying the same thing.
Okay, yeah, I get it.
We're in different ballparks here.
All right, thank you.
All right, peace. So this is because you're independently leaving the class. If each person could see how many were left, then we would approach 0 a lot faster. I don't know if that's from advertising mathematics or somewhere. If you get to see what other people are doing. All right, we're down to 9. Some of you must enjoy my voice. I like that. All right, I'm assuming the 3 people left don't have questions. I'm going to end our session.